All right, so looking at continuous probability now, so we've spent about a week looking at discrete probability. We are going to come back to discrete probability. What's the difference between, I guess, we'll start with all the way back in year 8 sort of stuff. What's the difference between discrete and continuous data? Not the sample size.
I didn't say that. That wasn't a video.
Yeah, so discrete is intervals. So it doesn't always have to be a whole number. More often than not, it is a whole number. Shoe size is an example of a discrete. Foot length is continuous. Why is foot length continuous? Because any person in the room, I could measure your foot and say your foot's 30 centimetres, 27. 27.5, says Brad. Well, I would argue that Brad's foot is not 27.5 centimetres long.
What size is that? Is that not?
It's
no,
27.4. It's 27.43244, and just keep going, correct? There is no value in which Brad's foot, I'll ever definitively say what Brad's foot length is.
No, that's where I measured this.
Okay, thanks, Brad. Your shoes on, so let's just. Good. So, your shoe size, however, there are people in the room that have got 9.5s, there are people that have got 6.5s, there are people that have got 6s. They go up in 6, 6.5, 7, 7.5, etc. So they're discrete, whereas our foot length is a continuous data point. Happy with that?
Yeah.
Important that we understand the first thing is the probability of continuous data equaling one set value is 0. So the probability that Brad's foot is 27.5 centimetres is 0. There is no chance that it's 20, because even if we pull out a ruler and it's got millimetres and Brad's foot length is exactly 2250, if we zoom in further, it's not going to be 2250,000,000. There's always going to be a point where it's off that, correct? So the probability of equaling an exact value is 0. So when we're dealing with these probabilities, we need a range of values, and they can come in a few forms, often like this. We can also have it represented like this, as an example. And what's that mean? We have a second bound, really, don't we? Negative infinity or the end of our function. Cool? Happy with that? So, we are going to start with probably the most complex component of this topic. I don't mind it because it gets us back to doing some integration and that sort of stuff. Yeah. But we can use probability functions, probability density functions. The area under those tells us about probability. Happy with that? So we can use a function to model probability by saying, well, this function represents my bell curve, whatever it happens to be. If I find the area between these two values, that will tell me the probability between those values. Cool? So obviously I said the word area under the curve, which means what process are we going to be using? Integration. Good. But before we go any further, let's look at probability density functions. What do we know about probability? What must the area of our probability density functions be equal to? Can it be 0.98?
No.
Can it be 1.32?
No.
It's got to be exactly 1. Must be equal to 1. If the area does not equal 1, it is not a probability density function. What must the function never do? Correct. Now, lots of functions cross the x-axis and they go negative, but we can cut them off if we use piecewise. So we just have to realign ourselves with piecewise functions. They often look like this. We've got our function is equal to, I'm just going to call it some function, gx, between two values. 0 otherwise. What does that mean? Why do we do that?
Do what?
Why do we have this bottom part here? We can't be negative, it has to be equal to 1, so do we have to cut our function very specifically and then say there's no function basically otherwise, it's just a line. Cool? So we don't really ignore that part of the equation, it's just saying that if we're outside this domain, nothing's happening. Cool?
Cool.
You can have multiple piecewise functions, you can have gx and then hx and then it'll finish with 0 otherwise. Awesome. So we're going to consider this probability density function to start with, and we'll go through an example. So we'll go through 2 examples actually, because I think we probably need 2 examples. Consider the probability density function fx equals sine x on 2 between 0 and pi. Determine the probability that x is less than pi on 2. So I'm going to start with p x is less than. Do I need the equal sign?
Yes.
Doesn't really matter. Why doesn't it matter? Because the probability of x equaling pi on 2 is
Always.
0, so it doesn't matter if we add it or not. Cool? So we don't have to be as precise with our equal signs when we're dealing with continuous data. When we're dealing with discrete data, do our equal signs matter? Absolutely. So we integrate this between, I'll leave that up for you to decide. No dramas there? What's my lower bound? 0. What's my upper bound? Very good. I'll just integrate that. For those of us who can't remember how to integrate, I'll do a little crash course here. Sine becomes negative cos. We've got no power inside the bracket, so we can just leave it as exactly the same as it was. We're just swapping it from sine to cos. We then sub our values in. So we get negative cos pi on 2 over 2 plus c minus negative cos 0 on 2 plus c. What happens to the c's?
Cancel.
Cancel out. What is cos pi on 2? Unit circle. Cos is our x value, correct? So what's our x value there? 0, so that's 0. We can put a line through that.
0, take 0.
Cos of 0 is 0.
No, 1.
1, so
1 and 2.
can I slow? Okay.
So yeah, in 1.
That's alright.
1 and 2 take away.
Are we happy with that step there? Sine becomes cos. Here, we're just subbing in our top bound and then our lower bound. And then the part where I was quick was talking about our unit circle. So we know that cos of pi on 2 is 0 because of our unit circle. We also know that cos of 0 is 1. We carry the two negatives, so what's the answer going to become?
1 on 2.
1 on 2.
Take 0.
We don't need to have units because it's a probability.
So you do need units.
So what's the probability of that occurring?
1/2.
Half, okay, which is 50%. What do we call the point where 50% of our data is above and 50% of our data is below? It's got a special name. Who thinks it's the mean?
That's a median.
It's the median, very good. That's our median.
Oh, yeah. Fist
Okay.
bump me, fist bump me.
Good.
There's 2 fist bumps on us.
So I'm just going to do a second example for the same one. So again, we are, and these are both text-free. It's a good chance for us to catch up on a few of our underlying skills here.